Hello everyone, welcome to Try Right, a new era of learning. This is Fact 365. In Module 3, we are discussing about Minimax algorithm in artificial intelligence. Let's begin the topic. Minimax algorithm is a decision-making algorithm used in artificial intelligence, particularly in games theory and computer games. It is designed to minimize the possible loss in a worst case scenario, hence min, and the maximize the potential gain, therefore max. So here we can see here the the minimax algorithm is a fundamental concept in AI, especially in advanced search problem where two or more players take turns and they one player gain in another player loss, zero sum games like that. So think of a game like chess and checkers and tic-tac-toes like that. So the basic behind the core idea is the algorithm is operates on a principle of looking ahead in the game tree and determines the optimal moves for the current player, assuming that the opponent will also play optimal involves two main concepts, which are maximizing and minimizing, right? So maximizing we call as min, and this phase is represented the opponent turns. The minimum player will choose a move that lead to the lowest possible. Okay, score for the max player. The goal is to maximize the or minimize the players. Okay, oh, sorry, players gain. So, here again we have the maximizing also. So therefore, max also we gain the potential gain, right? So this phase represents the current player turns. The max player will choose a move that lead to a highest possible score it makes, and themselves the goal is to maximize therefore their own. So here we have principle. Mm, Minimax algorithm is used in artificial intelligence in computer games. It also it's at the heart of the almost every computer board game, and Minimax chooses the path which the minimize the gain of the current player while minimizing the gain of the advisor. And a search tree is generated depth first search starting which is the current game position, so up to the end game position. So cannot work in real time, not turn based with timer iterative depending later. So here we have game tree, it has a game tree constructions and evolution functions and backtracking and minimizing and optimal moves. So it has lots of components to the which we use. Okay, instead the minimax algorithm is about to making a best possible decision for yourself, assuming your opponent will also play perfectly that towards the you. Okay, so where is the algorithm used? Like we can say applies to the games where players take turns, like we have some in chessboard, we take turns like that. So have perfect information like and the checkers and tactics. Most widely used in logic games. Those games are also called as zero sum games. Like a game in which gain of a player's moves is exactly balanced by the loss uh, incurred by the opponent's moves. Used in economic situations, used in social situations. So minimax algorithm component. So here we have search tree. In we have search tree, we have the square representation trees of like we call as square representation states. Also we can say after remove branches or the decisions and started root and node at end or the leaf nodes, right? So unlike binary trees, can have any number of children. So depends on the game situations. Levels usually called please, and each place is where it turn switches to the other players, right? So players called min and max. So min max algorithm description one. So here we can say assign a point to the outcome of the game. Tic-tac-toes, X win, the value of the one is zero wins, right? Zero wins value minus one. So max is the highest value. The max try to the minimize the point value with while min zero trials to the minimize the point value. So assume both players play to best of the ability. Always makes a move to minimize or maximize the points. So in choosing the max, will choose the best moves to get highest point. Assuming min will choose the best move to get the lowest point. So here the priority we have max players aims the aims to maximum their score or utility values. So choose the moves that lead to the highest possible utility value, assuming that opponents will play optimally, right? So here optimal moves like but the move from the current state to the lead state is the best to maximize the score after the considering all the future of possibilities. Like chosen as an optimal move, we can say. And minimizing players like aim to the minimize the maximum score or if utilities values select the move that result in the lowest possible utility value for the maximizer, assuming that the opponents will play optimally. So in diagramical way you can explain I can explain it. So okay, let's see the diagram. So we explain step by step. So for a step create a maximum node, right? So this is the very first step in significance, that starting point of the game representing the current state where the maximizing the players, okay, is about to make a decision. This node is typically the root node of the min max. So here we can say, so step two, uh, generation of children nodes mean using the EFS. So we can say from the initial max node, the algorithm explores all the possible moves that the max player can make. Each of those possible moves lead to a new game state, and this new state becomes the children node, right, of the current max node. So node A1 is generated, like the node A1 is generated to its neighbor. So from the node A1, which is a min node, so we are starting with max. We are going to min. Okay, min, max, min, like that we get. So we choose the min value here. So explore all the possible paths and the moves to the min pile player can make each of those moves lead to a new game state and becomes a child node. Okay. So A1, here we have step 4. Children of A1 are generated. Children of A1 are generated. We can see here. So node evolution takes place using the evolution function where like so node evolutions functions takes place using the evolution function. Values are filled in nodes, right? So this is a crucial step once the algorithm reaches the leaf node, right? So the deepest node is a tree that it explores within its seat set depth limit or terminal game state, right? So also known as heuristic functions, if applied, the function assigns a numerical utility value or score to each of those leaf nodes, right? The value represent how many favorable that particular game state is for maximizing players. For example, in chess, a positive value might indicate an advantage for a max player. A negative value is an advantage for the min player, like that. So step six. Now A1 choose the minimum of the two child nodes value. Okay, A1 chooses 7, 3. So if we want to choose the minimum value between the 7 and 3, right? So in that 7 and 3, we can consider the min value has our parent node is min, right? So we are choosing the min value here. So in between 7 and 3, we choose the 3. So the step iterates the min part of the min-max algorithm. Now starts the propagation values backup. Uh, like we can say the backtracking to the tree. Since A1 is a min node, it represents the opponent run turns. Okay, now it's back to the next turns. So it limits. So whenever you reach, like is the three, we wherever you choose, we choose to the parent node to that number. So like that, it repeats the step 3, 4, 2, 6 up to 3, 4, 5, 6. We repeat until the children of nodes A1, A2, A3 are generated. Right. So overall, my final step is the main node chosen to the max value of the children node is the value of the and this tells us the best possible moves to the which should. So here we can say that. So first this is we don't have it is a max value. So it is a min value. So it is a min, right? So in min, we want to consider average value, right? Both of the. So here we travel this and this. So we are backtrack again. So we have both numbers, right? We have 3 and 7. So this min value is 3. So we consider this 3 to the our parent node, okay? So like that. So again with backtracks, again it goes level by level, right? It goes level by level, right? when it backtracks and goes level by level. So it goes here to so 15. Now 15 has only one value, so it directly represent to the 15. So now it directly moves to the 1. So here why we take here we have 12 and 13 and 14, right? So here what we have here we have three both values, right? So in this way we have the one has the min value. Okay, so it consider one. Okay, so like that. So here what would we happen? So here we can say here we considering the lowest values because it is a min cycle. We can see this level two is the all min based nodes. Okay, but in level one it has a max based levels, right? So we in these we are considering here minimum values, and by the taking of minimum values, we are all those subnodes of the internal nodes of the tree from we take the max value. If we have min node, we take minimum value. If we have max node, so we take the maximum value. So here we have max node. So we want to assign this value, right? So in previously we did not assign this value. So we take for max node to max value to minimize the min value. So properties of minimax algorithm: complete, optimal, time complexity, and space complexity. So complete as tree is infinite, so it completes, it covers all the paths and the nodes of the, and it covers all optimals. Optimal, yes. Again, to optimal opponent, it can be can it be beaten by the an opponent playing as a sub optimally? No. It is a formula we have O of B of power M, O of B power M. So where M is depth and the B is the branching factors. So space complexity we have O of BM, like where depth first search generates all the actions at once. O of M means backtracking search and generate all the actions at one at time. So this is we can see the concept here. So like this here also we have a diagram. So like this we take the min and max here too. So we can see this is the max, right? This is the max. So this node is min node and this is max and this is min. So from the this is max. So how will we choose? So we choose from here. We come backtracking here. So it is a max node, min node, right? From max, we are choosing the this is min node. So like that, we will go first here because it is max value, right? So it is choose max. So for the downwards, we come from the leaf node, right? From here come from the leaf node. So for the five, we it is a min node, right? We choose as the min value to the five, and again we backtrack to the don't assume this numbers is existed. I am drawing line by line. So this is 4, right? For the 4, min value is 4. For the min node, it takes 4. So like this we have both. So this is the max node. Please take max value. So 5 will be assigned here. And it is min node. 5 and 3, it has a min value. So it takes minimum value. And it is max value. 3, 5, 6, it has a max value 6. Like that it represents. So it are the steps involved in min-max algorithm. The min-max algorithm involves the several key steps executed recursively until the optimal move is determined. Hence, we have step-by-step breakdowns. Step 1, generate the game tree. Objective, create a tree structure representing all positive moves from the current game state and detail. Each node represents a game state and each stage represents a possible move. Have evaluate terminal state objective, assign the utility values to the terminal nodes of the game tree. Detail those values represent the outcome of the game, win, loss, or draw. Step 3, propagate the utility value upwards. We have the starting from the terminal nodes and propagate to the utility value upward the to the tree. And in details, for each non-terminal node, if it's the maximum player's turn, select the maximum value of the child node, right? Like we select for the min to min values and max to max value. If it is the minimizing player, turn to the select the minimum values for the child nodes. So select optimal moves. At the root of the game tree, the maximizing players select the move that lead to a highest utility value. So here also we can see some little bit reason. So we can say random. It is a random uh, min max or all such releases. So it taking min values here from the leaf. So it enters the min values in the both subnodes, and in that which has max value, it takes the 12 to the max node. So like the perfect move calculated, ever human error not taken into the account. These are randomness. So like that we have again. So in this also random minimax CPU random moves like case one infinity optimal maximum strategy and case two random strategy for current. So it directly entered one value. So if we have reverse like greater than, like if we take the min and up min, so downwards we can see average like greater than or equal to like the average values we can consider here 10, 7, like 12, like that. So like if we like that we move, then we get the wrong step because if we take here we have to min value to greater than equal to 9, right? So we are choosing 10. So here we have wrong pickup move. So for the pike, right pickup move is 9 here. So it gets wrong moves. So the correct move is to 12. So if you take like this, if the max value get also correct value. So this is wrong move, obviously, right? So this is CPM move. So note the CPU does not play optimal moves because it is R min max. So I hope you guys all are understand about this min max such algorithm topic. So thank you.